4.5 billion years ago, a Mars-sized planet called Theia slammed into Earth at unimaginable speed, turning both worlds into a molten hellscape of vaporized rock and superheated metal. The collision gave us our moon and fundamentally changed Earth's chemistry forever. But here's the mystery scientists just cracked. Where did Theia come from? And the answer is shocking. It was our neighbor. Theia formed right next door to us, possibly even closer to the Sun than Earth itself. We've been orbiting the debris field of a planetary murder scene this entire time. Welcome to Mind and Marvel, where we decode the most mind-bending discoveries about our universe and the cosmic events that shaped our existence. Today's story is about one of the most catastrophic and consequential events in our planet's history. It's called the Giant Impact Hypothesis, and it explains how Earth got its moon. But the details of this cosmic collision have been hotly debated for decades. Here's what we know happened. About 4.5 billion years ago, during the chaotic early days of our solar system, Earth wasn't the mature planet we know today. It was Proto-Earth, a young, still-forming world made of accreting dust, rock, and metal. And into this developing planet crashed Theia, an object roughly the size of Mars. The impact was so violent that both planets melted, rock vaporized, metal liquefied, the energy released was incomprehensible. And from the debris field that resulted, a ring of molten rock circling what remained of Earth, our moon formed. This theory was first proposed in the 1970s, and it's been the leading explanation for lunar formation ever since. But there's always been a nagging problem. Where did Theia come from? You see, different parts of the solar system have different chemical signatures. Think of it like regional accents in language, but for rocks. Objects that form in the inner solar system, near the Sun, have different isotope ratios than objects from the outer solar system. It's because the giant molecular cloud that formed our solar system wasn't perfectly mixed, like poorly stirred cake batter, as scientists describe it. So if scientists could figure out Theia's chemical signature, they could trace where in the solar system it originally formed. Was it from the inner solar system, close to the Sun, from the outer solar system, beyond the asteroid belt, or from some completely different region? The challenge? Theia doesn't exist anymore. It was destroyed in the collision. So how do you study a planet that no longer exists? Enter researchers from the Max Planck Institute for Solar System Research and the University of Chicago. In a study published in the journal Science in November 2025, they finally cracked the case using an ingenious approach. They analyzed isotope ratios from Earth rocks, moon samples, and meteorites to reconstruct Theia's chemical fingerprint and deduce where it came from. And what they found rewrites the story of Earth's formation. To understand how scientists tracked down Theia's origins, we need to talk about isotopes. And don't worry, I'll make this as painless as possible, because isotopes are actually fascinating once you understand what they tell us. An isotope is just a version of an element with a different number of neutrons. Take iron, for example. Most iron atoms have 26 protons and 30 neutrons, but some iron atoms have 28 neutrons instead. Same element, slightly different weight. These are different isotopes of iron. Now here's the key. When the solar system was forming from a giant molecular cloud, that cloud wasn't perfectly uniform. Certain regions had slightly more of certain isotopes than others. As planets and asteroids formed from material in specific regions, they inherited those regional isotope signatures. It's like how different vineyards produce wine with slightly different flavors based on their local soil chemistry. The terroir of space, if you will. Meteorites that fall to Earth are incredibly valuable for this research because they come from different parts of the solar system. Some meteorites, called non-carbonaceous chondrites, formed in the inner solar system relatively close to the Sun. Others, carbonaceous chondrites, formed in the outer solar system beyond the asteroid belt. And here's what's been puzzling scientists for decades. When we analyze rocks from Earth and rocks from the Moon, their isotope ratios are eerily similar, almost identical in fact. This was actually a problem for the giant impact theory. Think about it. If Theia came from some distant part of the solar system and slammed into Earth, you'd expect the Moon, which formed from debris from both planets, to have a mixed signature, showing contributions from both Earth and Theia's distinct chemistries. But that's not what we see. Earth and Moon have nearly identical isotope signatures for most elements. Some scientists argued this meant maybe Theia came from the exact same region as Earth, essentially a planetary twin. Others suggested maybe the collision was so violent that it completely homogenized everything, mixing the materials so thoroughly that distinct signatures were lost. the new study took a different approach, led by Timo Hopp, a geoscientist at Max Planck Institute. The team analyzed isotope ratios for multiple elements: iron, chromium, calcium, titanium, and zirconium. They looked at lunar samples returned by Apollo missions, terrestrial rocks from Earth, and meteorites from known locations in the solar system. What they found was striking. The moon's chemical signature matched Earth's almost perfectly. But here's the critical insight: that shared signature also matched the signature of inner solar system meteorites, not outer solar system ones. This was the smoking gun. If both Earth and Theia have similar signatures, and that signature matches the inner solar system, then both planets must have formed from inner solar system material. Hopp concluded, the most convincing scenario is that most of the building blocks of Earth and Theia originated in the inner solar system. Earth and Theia are likely to have been neighbors. In fact, the data suggests something even more specific. Theia may have formed even closer to the Sun than Earth did. Think about the implications of that. Earth and Theia weren't strangers from opposite sides of the solar system. They were planetary neighbors, possibly orbiting in similar regions, formed from the same primordial materials. The poorly mixed cake batter of the early solar system meant that material at different distances from the Sun had slightly different compositions. By matching Theia's inferred composition to that specific flavor of material, scientists pinpointed where it formed. It's detective work on a cosmic scale, using chemistry to solve a 4.5 billion-year-old mystery about a planet that no longer exists. Now that we know where Theia came from, let's talk about what actually happened during the collision, because this wasn't just any impact. This was one of the most violent events in Earth's entire history. Picture this: 4.5 billion years ago, Theia, roughly the size of Mars, which means about half the diameter of Earth, collided with proto-Earth, turning both into a molten mess of rock and metal. To give you a sense of scale, Mars has a diameter of about 6,800 kilometers. Earth's diameter is about 12,700 kilometers. So Theia was massive, not just an asteroid or comet, but a full-fledged protoplanet with its own core, mantle, and possibly even an early atmosphere. When these two worlds collided, the impact angle and speed were crucial. Scientists believe Theia didn't hit Earth head-on like a cosmic car crash. Instead, it struck at an angle, a glancing blow that was still absolutely devastating but allowed some of the material to survive, rather than being completely obliterated. The energy released would have been beyond comprehension. The surface of both planets instantly vaporized. Rock turned to superheated gas. The temperature spiked to thousands of degrees. The impact created a debris field, a ring of molten rock, vaporized material, and fragments circling what remained of Earth. Proto-Earth survived, but it was fundamentally changed. Its day was shortened. The impact transferred angular momentum, making Earth spin faster. The impact also tilted Earth's axis, though later gravitational interactions would modify that tilt further. And from that debris ring, over the course of thousands or millions of years, the Moon formed. Material in the ring began to clump together through gravitational attraction. Larger chunks pulled in smaller ones. Slowly, a new spherical body took shape. Our Moon. Here's something fascinating. The giant impact explains several strange features of the Earth-Moon system that puzzled scientists for centuries. First, Earth's unusually large moon. Most planets in our solar system either have no moons, or their moons are tiny compared to the planet. Mars has 2 tiny moons that are basically captured asteroids. Venus has none, but Earth's moon is huge relative to Earth. It's about 1/4 the diameter of our planet. That's unusual and suggested Earth's moon formed through some extraordinary process, not just capture or co-accretion. Second, the moon's lack of iron. The moon has a very small iron core compared to Earth. Earth's core is about 30% of the planet's radius. The moon's core is only about 20%. Why? Because most of Theia's iron core and Earth's iron core sank to the center of the reformed Earth during the post-collision period when everything was molten. The moon formed mostly from mantle material, the rocky outer layers of both planets that were ejected into orbit. Third, the moon's orbit and rotation. The moon is slowly drifting away from Earth at about 3.8 centimeters per year, roughly the rate your fingernails grow. This is because tidal interactions between Earth and Moon transfer angular momentum. The giant impact set up the initial conditions for this orbital relationship. Fourth, Earth's water. This is still debated, but the giant impact might have stripped away much of Earth's primordial atmosphere and surface water. If so, the water we have today arrived later, delivered by comets and water-rich asteroids. Though some recent research suggests some water might have survived in Earth's mantle even through the impact. The collision also explains why Earth's mantle contains more iron than you'd expect if Earth formed in isolation. Scientists note, it stands to reason that much of the iron now found in Earth's mantle must have arrived after the planet's reformation, delivered perhaps by a world-shattering cosmic impact. Theia wasn't just an impactor, it was a building block. Earth today is literally made from the combined material of two planets. And here's something that sends chills down my spine. Every time you look up at the moon, you're seeing the monument to this ancient catastrophe. The moon is the remnant of the most significant collision in Earth's history, orbiting us as a permanent reminder of the violent chaos that characterized the early solar system. So, scientists have figured out where Theia came from, but here's where the story gets even more interesting. Theia didn't completely vanish. Pieces of it are still inside Earth today. Remember, this was a collision between two massive bodies. While much of the debris formed the moon, a significant portion of Theia's material merged with Earth. Theia's core likely sank into Earth's core. Theia's mantle mixed with Earth's mantle, and some scientists believe they've found the biggest remnants of Theia still hiding in Earth's interior. Two mysterious structures called Large Low Shear Velocity Provinces, or LLSVPs. These are massive blobs of unusually dense material sitting at the bottom of Earth's mantle, right above the core. One is beneath Africa. The other is beneath the Pacific Ocean. Each one is about the size of a continent and reaches up to several hundred kilometers into the mantle. We know they exist because of seismic waves from earthquakes. When earthquake waves pass through these regions, they slow down dramatically, hence the name low shear velocity provinces. This tells us the material is chemically different from the surrounding mantle. Scientists have debated what these blobs are for decades. Some propose they're remnants of ancient tectonic plates that sank deep into the mantle. Others suggested they're pockets of unusually hot rock. But one of the most intriguing theories is that they're literally chunks of Theia that survived the collision and have been sitting at the bottom of Earth's mantle for 4.5 billion years. Think about that. We might be walking on top of the remains of an entire planet that crashed into ours before life existed, before oceans formed, before Earth even had a stable crust. These blobs aren't just geological curiosities, they might be affecting Earth's behavior right now. The African blob, in particular, has been linked to a weakening of Earth's magnetic field over the Atlantic Ocean, a phenomenon called the South Atlantic Anomaly. Scientists also think the blobs might influence how Earth's tectonic plates move and where volcanic hotspots form. The new study about Theia's origins adds critical context to this theory. If Theia formed in the inner solar system from material similar to Earth's, then its density and composition would be consistent with what we observe in the LLSVPs. It strengthens the case that these mysterious structures are indeed the fossilized remains of the planet that gave us our moon. But this discovery also has broader implications for planetary science. First, it tells us that planet-on-planet collisions in the early solar system weren't random events between objects from wildly different regions. Instead, neighboring planets could form in similar zones and then collide due to orbital instabilities. This matters for understanding how other planetary systems form and evolve. Second, it suggests that violent collisions might be a normal part of planetary formation, not a rare catastrophe. Earth might not be special in having experienced a giant impact. Other rocky planets in other star systems might have similar formation stories. Third, it helps explain Earth's unique characteristics. Our large moon, our rapid rotation, our magnetic field, our plate tectonics, all of these might be consequences of the Theia impact. Earth without Theia would have been a fundamentally different world, and without the moon's stabilizing gravitational influence on Earth's axis, our climate might have been too chaotic for complex life to evolve. In other words, we might owe our existence to this ancient cosmic catastrophe. The researchers note, The momentous clash between neighbors gave us our moon, which has been drifting away ever since and is currently distancing itself from Earth at a sloth-like rate of 1.5 inches, 3.8 centimeters, per year. Every year, the moon gets a little farther away. Eventually, billions of years from now, it will drift far enough that total solar eclipses will no longer be possible. The perfect alignment we enjoy today, where the moon appears almost exactly the same size as the sun in our sky, is temporary, a cosmic coincidence resulting from where we are in the moon's ongoing departure. So when you look up at the moon, remember, you're seeing the product of a planetary collision that happened before Earth even had solid ground. You're seeing the aftermath of an event so violent, it melted 2 entire worlds. And you're seeing a natural satellite that's slowly, gradually leaving us, carrying with it the memory of Theia, our forgotten planetary neighbor. Before we wrap up, let's talk about how scientists actually do this kind of research, because the methods are as fascinating as the findings. This study relied on isotope analysis, measuring the precise ratios of different atomic versions of elements. This requires incredibly sophisticated instruments called mass spectrometers that can detect differences in isotope abundance down to parts per million or even parts per billion. The moon rocks used in this study came from the Apollo missions, lunar samples returned between 1969 and 1972 that are still providing groundbreaking insights more than 50 years later. These samples are treated like the scientific treasures they are, with only tiny amounts released for studies. The meteorites came from collections built over decades of hunting for fallen space rocks. Scientists can determine where in the solar system a meteorite formed by comparing its composition to theoretical models and other samples. It's important to note that while this study provides compelling evidence for Theia's inner solar system origin, science is always open to revision. Future studies with more samples, more sophisticated techniques, or new theoretical insights might refine our understanding further. What we can say with confidence is that the giant impact hypothesis remains the best explanation for the moon's formation, and this new study has answered one of the biggest remaining questions: where Theia came from. The fact that scientists can reconstruct the origin of a planet that was destroyed 4.5 billion years ago using samples from Earth, the moon, and meteorites is a testament to the power of chemistry and the ingenuity of planetary science. And there you have it, the incredible story of how scientists finally traced the origins of Theia, the Mars-sized planet that collided with Earth 4.5 billion years ago and gave us our moon. Let's recap the key discoveries. By analyzing isotope ratios of iron, chromium, calcium, titanium, and zirconium in Earth rocks, moon samples, and meteorites, researchers determined that Theia formed in the inner solar system, not from some distant region, but right here, close to the Sun, possibly even closer than Earth itself. Earth and Theia were planetary neighbors before their catastrophic collision. The impact turned both worlds into a molten hellscape, but from that chaos emerged 2 objects that would be locked in an orbital dance for billions of years: Earth and its moon. Pieces of Theia are still inside Earth today, possibly forming the mysterious blob structures at the base of our mantle. This research, published in Science in November 2025 by Timo Hopp and colleagues from the Max Planck Institute and the University of Chicago, solves a mystery that's puzzled scientists since the giant impact hypothesis was first proposed in the 1970s. Every time you see the moon in the sky, remember, you're looking at the remnant of the most significant collision in our planet's history. You're seeing proof that Earth's story is written in cosmic violence, chaos, and ultimately, the creation of the stable world that allowed life, and eventually, us, to emerge. The moon is drifting away at 3.8 centimeters per year. In the cosmic timescale, our perfect view of total solar eclipses, where the moon covers the sun just exactly, is temporary. We're living in a special moment in Earth's long history. If this deep dive into planetary science and the violent birth of our moon fascinated you, I need 3 things from you. First, hit that like button. It helps us reach more people who love learning about the cosmos. Second, subscribe to Mind and Marvel and turn on notifications so you catch all our breakdowns of the latest discoveries about Earth, space, and the universe. And third, drop a comment. What other cosmic mysteries should we explore? Are you more interested in the early solar system, exoplanets, or the future of our moon? Thanks for watching, Curious Minds. Until next time, stay curious, stay awestruck, and remember, we're all living on the fusion of 2 ancient worlds, orbited by the monument to their collision. The next time you see the moon, you're seeing Theia's legacy. And that's pretty damn amazing.